going to start going through today's lecture, but we've spent a lot of time in the last couple of classes talking about this idea of fixing states on a table and, what we're supposed to do, all this linear interpolation or double interpolation. I think it's important to kind of remember or remind ourselves why we care about thermodynamics, right? This is a foundational course in mechanical engineering, right? And we're interested in this idea of energy transfer, how we turn heat into work, right? So we like this topic as mechanical engineers because turning heat into work is a lot of what we do here in mechanical engineering, right? So, thermodynamics covers things from coal-fired or nuclear-fired power plants, gas-fired power plants, automobiles, airplanes, all of these things. The core of all of these technologies is something called a heat engine, right? And the purpose of heat engines is to take heat, right, typically from burning things, right, and turn that into mechanical work, right? Whether that's a spinning turbine that powers a jet plane, wheels spinning on a car, right, or actually turning the drive shaft, which eventually turns the wheels on your car, or turning a shaft in a power plant, which ultimately is creating power using an electric generator. I think another neat thing that we'll learn in this class is kind of how to do all of this in reverse, right? How to trick the universe, almost bend the universe to our will, right? Because typically we know in the universe, not just typically, but all of the time in the universe, heat transfers from a place that's hot to a place that's cold. Heat always moves from hot places to cold places. So as mechanical engineers, understanding thermodynamics, eventually someone came up with a design for a piece of equipment that makes a cold side of the device and a hot side of the device, so that the cold side ends up being colder than the place you want to keep cool, right? Maybe it's now maybe you're running your air conditioner in your house, although it's been a little bit cooler this week, right? Or in your refrigerator, you want to keep the air in the refrigerator colder than the room that the refrigerator's in, so you build a fridge which has one part in it that's even colder than the fridge, right? And then another part, the back of the fridge, it gets hot, right? Or a window air conditioner, if you ever sort of see the exhaust air that's going outside, it's hotter than the room, right? So these devices have a hot side and a cold side. And, so by doing this, mechanical engineers have figured out how to kind of trick the universe or bend the universe to our will in order to sort of do something that doesn't seem like it would be possible on its face. So what I like to think about is for each one of these very complicated systems or cycles, they're made up of individual processes, right? We've talked a little bit about processes and using the first law, right? So in a nuclear power plant, for example, we have a boiler. Boilers are important, right? Because this is the idea that, you give a mechanical engineer heat and what we want to do is boil water, right? So that's our boiler, right? We like that because it makes that water expand. And when it expands, we run it through a turbine. And as it expands over the fan blades in the turbine, it makes that shaft spin, right? So this is kind of the part that we want, right? This gives us the work that we're trying to get. The problem is now we have some steam and it's not particularly useful for anything. So what we do is we cool it back down. We cool this steam back down to a liquid, right? In something called a condenser, because we're making that steam condense into a liquid. And then when we have liquid water, it's not that energy intensive to increase the pressure. And then we do that with a pump, right? So we take that liquid water, we increase the pressure, right? And then we're back to having this high pressure fluid that we run through our boiler. And then at state 2 here, we get high pressure, high enthalpy steam, right? So that's the energy, and we harvest that energy through a turbine, and we keep doing this again and again and again, and that's what's called the thermodynamic cycle. And it's a cycle because it keeps going around and around and around. And all of these cycles are made up of these individual processes that we kind of chain together like this, right? And maybe it's because I'm, I like to break things down into something that's simple, something that I can understand, but I like to think about all of these processes or all of these cycles as sort of putting together Lego blocks to make something cool, right? So each one of these Lego blocks is a process, right? So in this case, This pump provides a process, the boiler provides a process, the turbine does, and so does the condenser. So each one of these are like Lego blocks, and we put them together to make something cool like a power plant. Right? So we've started to try to understand individual processes in this class with the first law. But in order to understand the individual processes, we have to understand the individual state points. Because all of these processes, what we're trying to do is store energy inside some kind of a material, right? Or maybe harvest energy from some kind of material. So in order to do that, we have to know how much energy is in the material, right? That's the left-hand side of our equation, the change in the energy inside of our control volume. So we need to be able to fix states, right? That's like finding the pips on our Lego block here, right? So I know it might feel a little bit tedious or a little bit boring, but we're building up to being able to do something that I think is really cool. And the neat thing, I think, about being a mechanical engineer and about applying thermodynamics is that if you understand how these processes work, then you can take a very complicated system, like a power plant, and you can modify how you chain these processes together. And you can do that in ways that will give you more power, or maybe will produce less emissions, right? So this is kind of our way of sort of contributing to the societal goal of consuming energy, because I mean, we can show sort of on the history of humanity that consuming more energy has led to more prosperity, but there's a cost to that. So if we can try to limit things like emissions from the generation of things like power, then I think that that's one way that mechanical engineers can sort of contribute to the well-being of society. Unfortunately for us at this point, part of this process has been, well, what happens when we're trying to figure out what's going on in these compressed liquids? So maybe you've looked at these compressed liquid tables and you've seen that it's a lot more sparse. There's a lot less data for compressed liquids than there are for, say, superheated vapors. And, there's maybe two reasons for that, right? One of them could be that just the people who were making the textbook were cheap and didn't want to put a lot of tables in there, right? But if we assume that they're logically going about their business, right, then I think what we might assume then is that some of these properties are not strong functions of pressure, right? Or maybe that there's other ways for subcooled liquids that we can approximate these properties, so maybe we don't need the tables as much as we do for things like steam. Right? So we went through this and we figured out how to do this. We felt pretty good about ourselves. We did this double interpolation. We made this extra table, right? Here we made our own table here at this intermediate pressure, right? We filled in some values, but so that then we got our first interpolation with pressure, but then we wanted to get another interpolation with temperature, because this temperature that we wanted was in between 40 and 60, right? So we needed another interpolation factor, which we backed out because we knew the enthalpy in this sixth state that we did in the example last class, right? And then we used this second interpolation factor to find the specific volume and the specific internal energy at state 6, right? And all that was pretty tedious work, right? But we did feel good about it, right? Because we filled in our state table, and if we were going through sort of the analysis of a power plant or something, then we would have had the information that we needed, right? So, we felt pretty good about doing this because it helped us fix all the states, right? But today, we're going to talk a little bit about a way that we can shorten up that process, right? Because that double interpolation is pretty tedious, right? So to go through all that mathematics, if we can kind of short circuit that process and still get a pretty valid answer, right? Then I think that's something that we'll all be a fan of. So just to sort of bring it back, right? We're trying to understand the first law, how energy gets transferred in these closed systems. We have to ask a question, what's in our system? So far, we've been talking mostly about water, but we'll move to ideal gases in the next class. Then we have to ask ourselves, well, is our system an open system or a closed system? Right? And typically, well, not typically, I guess exclusively up until this point, we've been talking about closed systems, but we'll move to open systems pretty soon as well. And then because it's a closed system, we know that when we're trying to describe what happens in the system, we use the closed version of the first law, that the change in energy of the material in our system is equal to the heat in minus the work out. We can make some assumptions about the change in energy of the system, typically that the changes of things like potential energy, kinetic energy, or spring energy in our system aren't as important as the change in the internal energy. So when we do that, the left-hand side of our equation becomes delta U, and the right-hand stays as Q minus W. We talked about work being the integral of pressure times dV, with a change in volume. We know that delta big U, the change in the internal energy, is equal to the mass times the change in the specific internal energy. And if we could find that, then we could use the first law to find how much heat is transferred either into or out of our system. We were at this point where we didn't really know how to find the change in internal energy, right? But we've learned through the last couple classes that we can use tables to do this. If we have some mixture, if we're under the vapor dome, so we have some mixture of saturated liquid and saturated vapor, then we can use tables A2 and A3. And typically, if we're trying to do this under the vapor dome, hopefully we'll be given quality because that makes our lives a little bit easier. But if we're given another property, like say specific volume, then we can use the specific volume to try to find quality and then use quality to find something like internal energy. If we're trying to find the energy that's stored either in a liquid, we'd use table A5, or in a vapor or superheated vapor, we'd use table A4. And in these sort of regions of our plot, temperature and pressure are independent. So we can fix the state with just the temperature and the pressure. Typically, we'd look on, say, table A4. We'd try to find the right subtable that has the correct pressure. And then maybe we'd use temperature to try to interpolate to find whatever values of properties that we need, right? So here we maybe need to find the interpolation factor A. And if we use A, we can set this equation up to look just like the quality equation if we find our interpolation factor A. And then we can use that to find things like specific internal energy or specific volume or specific enthalpy or any other property on the table. It gets a little trickier, like we've said, when we're looking at these subcooled liquids, because here the data is pretty sparse, right? There's not a lot of subtables when we're talking about subcooled liquids. So we'd have to kind of go through a lot of effort to make our own subtable at the right pressure, right? Maybe we'd have to do some kind of double interpolation where we're trying to interpolate both with pressure and with temperature. And I think for most of us, we'd prefer not to do this, right? Like it's like right now, we're doing a lot of homeschooling. My daughters, both of them, would prefer not to do their writing homework, right? So it's always like, do I have to, right? And it's kind of like double interpolation's a little bit like that because it's sort of a pain. It's not that any individual part of that problem is necessarily difficult mathematically, but just going through it is a very tedious process. And if you're like me, if I'm doing a lot of tedious work, I find my chances of clerical errors tend to go up. So today we're going to talk about strategies where for subcooled liquids, maybe we don't have to go through this idea of double interpolation. So it's not always necessarily to do double interpolation. And in order to get there, first we're going to talk about this idea of specific heats. So specific heat is defined as, well, there's two different kinds of specific heat. There's CV, so this is the specific heat at constant volume, so that's why the subscript is V, or you can have specific heat at constant pressure, which is CP. Now, if you're dealing with incompressible liquids or solids, then these equations are these values for specific heat are fairly constant. They don't change very much. So if that's true, then maybe we can come up with an equation where we can find the change in, say, specific internal energy as a function of temperature. So here, if we look specifically at the definition of specific heat at constant volume, we can rearrange this equation to say that C times dt is equal to du. right? So if we integrate both sides, then we'd come up with this equation here, right? Now, the cool thing about these incompressible fluids or solids, so we typically, if we're talking about liquids or we're talking about solids, it's not unreasonable to say that CV is constant. And if CV is constant, then we can pull it out of the integral, and our equation looks like this. Now we can integrate both sides. So the integral of dt is just delta t, and the integral of du is just delta u. So we get something that looks like this, that the change in the specific internal energy, if we have a solid or if we have an incompressible liquid, is going to be equal to CV times delta t. So this equation is pretty good. It totally breaks down if we start to boil our liquid. So this equation is good if the two state points that you're talking about are both liquid state points. So you're going from one liquid to another liquid, right? Maybe you're changing the pressure or you're changing the temperature. You can use this equation, right? But it doesn't work if you start to boil your substance. So this equation is only good if we have liquids or solids. It doesn't work for vapors or transition from liquid to vapor. We can apply the same thing. Sorry about that. We can apply the same idea, right? So if delta little u is equal to CV times delta t, but in my first law, I want delta big U, right? So then I multiply that by mass, so mCV times delta t. Right? I can apply the same thing for enthalpies. If we were ever interested in finding a delta H, then I can use the same process that I've used here with the definition for CP. I put this in here, and I can see that delta, the change in specific internal or specific enthalpy, delta little h, is equal to CP times delta T. Right? So that may become important for us as we move on in the course. Right? So again, it's important to remember that this is for incompressible substances. Right? So this is for liquids. It works for solids. And if we have an incompressible substance, one of the cool things is that CV and CP are the same thing. So that the numerical value of these two parameters are the same if you're talking about liquids and you're talking about solids. As we start to talk about ideal gases, then they become different. So it's important to split these out. So it's important to kind of remember a little bit which version of specific heat goes with which equation. So for me, I remember that CV goes with delta U because the V looks a little bit like a U, right? And then I had a student in my second year teaching this, and she said, oh, I remember that CP goes with H because H is enthalpy, right? So there's like the sound P at the end of the word, so then enthalpy goes with CP, right? So however you choose to remember it, that's fine. But remember that delta U goes with CV and delta H goes with CP. So if we used this idea, right? So let's say we had state 6, which we were trying to find before. We know that the temperature was 41.8 degrees, and we had a specific internal energy that we ended up getting by double interpolation. So here, if I kept the pressure the same, right, then I could find what U is pretty easily by looking at the table. I think it's either A2 or A3, the one with pressure on the left. So I could find the saturation temperature associated with 80 bar. So basically, what temperature does water boil at if I was at 80 bar? So now I would have two states, and they're both liquids, right? So one is a saturated liquid and one is a subcooled liquid, right? But they're both liquids. So if I did this, I could look this up on either table A2 or A3 pretty easily, find that the temperature here is 294.1 degrees Celsius, and I know that UF, which I look up on that same table, is 1305.6 kilojoules per kilogram. So then I could move between these 2 points. Because they're both liquids, it's okay to do this. I could see that delta U is equal to CV times delta T, right? And if I did this, I could look up in the textbook, okay, what's the value for CV of water? And it's about 4.38 kilojoules per kilogram Kelvin. So that means, it takes a reasonable amount of energy to increase 1 kilogram of water by 1 degree Kelvin, which is the same as 1 degree Celsius, right? And I put that into my equation, and I can see, right, from this, if I was moving from this state point down to here, I could say that U6 would be equal to UF minus CV times delta T, right? Because I have the drop in temperature. Here, the temperature was 294.1 degrees, and down here, it's 41.8 degrees. So I could put that delta T in there, and I can see that I get a value for U6 of 200.5 kilojoules per kilogram. So this is not a terrible approximation, right? We made some assumptions, so our answer is less right than it was when we were doing double interpolation, and we're within 15%. So this is not a terrible way to go, right? It gives us an answer that's in the right ballpark. It's not the right answer, but the answer from any kind of model is not the right answer, because every time you make an assumption, you take a step away from the real answer. Right? But maybe you're looking at this and you're saying, well, 15%, it's not the worst, right? But maybe there's a way we can do even better than this, right? So what if we don't want delta U? What if I just want U, right? Is there a way that I can get an approximate value for the specific internal energy if it's a liquid and I know the temperature? And it turns out that for a given temperature, the specific internal energy at that temperature for any subcooled liquid it's reasonable to approximate that as being the same as the specific internal energy for a saturated liquid at the same temperature. Right? So if we check this out, right? So these are values that I found, right? So if the pressure is 1 atmosphere and my temperature is 100 degrees. So this is actually the boiling temperature of water for 1 atmosphere. And I can look up on the table what my specific internal energy is. If I increase the temperature to 25 bar, I can still find what the specific internal energy at 100 degrees Celsius and 25 degrees is, right? But if I, here you can see that in that case, it's 418.24 kilojoules per kilogram. That's pretty close to 418.94, right? This is only 0.2% off. So it's pretty good if my pressure is 25 bar. If I increase my pressure again to 50 bar, my assumption's still pretty good if I do this. Right now I'm off by 0.3%. 0.3% is pretty low, right? It's almost the right answer. 75 bar, I'm off by 0.5%. 100 bar, 0.7%. 150, just over 1%. 200 bar, just over 1%. 250, approaching 2%. 300 bar, right? So this is like a 300-fold increase in the pressure. And our uncertainty went from 0% to 2%. So if you're trying to find the specific internal energy of a liquid and you want a very accurate answer, this is a pretty good way to go about doing it without doing double interpolation. So here you can assume that the specific internal energy of a subcooled liquid at a given temperature is approximately equal to the specific internal energy of that same fluid if you took the saturated liquid at that same temperature. This is not just true for specific internal energy. You can make this same approximation for specific enthalpy, for specific entropy, and for specific volume. So in all of these cases, you'll get relatively low uncertainty, and you'll have a process that's pretty easy to do, right? So the accuracy is actually even better if you do this versus if you do the CV times delta T approximation. Although both are going to be reasonable in different applications. Right? So here we had our state point, right? State 6, where we knew we did the double interpolation and we found U6 was 174.7 kilojoules per kilogram, right? If instead we said, okay, we knew the temperature here, so if I approximated my state point as being here on the saturated liquid line at the same temperature, then my UF, which would be my approximation for H or U6, would be 174.9. That's pretty close to 174.7, right? And my approximation for HF is also still pretty good, although larger than the uncertainty or the error in the specific internal energy. So we're going to use, or at least you're welcome to use, this approximation for subcooled liquids, right? And we're doing that by assuming that it's an incompressible liquid. So here in both of these cases, our error by doing this is relatively low. So this is why it's always important as you're an engineer and you're working through a problem, you always want to track your assumptions. We're really going to kind of hammer that home throughout this course, because when you track your assumptions, we're going to use different equations or different methods of finding the different properties of fluids, and they're all going to hinge on the assumptions that we make. So when you track your assumptions, it means it's easier for someone in the future to look back at your work. And that someone in the future is often you. Maybe your supervisor asks you a year ago about some, project, or a year in the future about a project that you did, right? And you're like, oh, I don't remember, right? Because my human memory is only what it is. But by writing things down, then you know what you did, right? As an undergraduate, it's also, it's useful to know that it makes grading your papers easier, right? So, if you write down your assumptions, because your assumptions are what justify the method that you end up using, right? So if you're talking about incompressible assumption, right, it's nice because it makes our lives easier. We don't have to do double interpolation anymore. The bad part, any assumption, right, any assumption that you make, right, is you walk a little bit further away from the reality, right? So that's true in this case too. So it means your solution has a higher degree of uncertainty, but in this case, that uncertainty tends to be fairly low. So this is a reasonable assumption to make in many practical applications. But again, if you want to maximize your accuracy, then you would do something like double interpolation. Although even that, like we've said, is you're linearizing a nonlinear function. So even that is not perfect, right? There's still uncertainty involved in that solution as well. So the other good part, I guess, about this, and I've said this already, but this is a reasonable thing for you to do in many different applications, right? But you're always sacrificing accuracy, but in this case, the sacrifice is fairly small. So before we get to an example, does anyone have questions about how we might use specific heat in different problems? Okay, we will carry on with this example. This is from the textbook 3.89. This handout can be found on the My Courses webpage, as we said at the beginning of the lecture, but I can read it to you as well. So we have a problem here shown in 3.89. We have a system that consists of a copper tank with a particular mass and 4 kilograms of liquid water. An electrical resistor, which we see here, has negligible mass. The system is insulated on the outer surface. That, I think, is this kind of speckled gray part on the outside. That's like insulation, right? Initially, the temperature of the copper is 27 degrees and the temperature of the water is 50 degrees. The electrical resistor transfers 100 kilojoules of energy into the system, and then eventually the system comes to equilibrium, which in this case means the temperature everywhere is going to be the same. And we're asked to find that equilibrium temperature. So this problem, like all other problems we'll do in this class, we can apply kind of the solution method that we're using here. First, we write down the information that we know. We're told that the copper mass is 13 kilograms, that the mass of water is 4 kilograms, that the mass of the resistor is so small compared to these other masses that we're tracking that it might as well be zero. It's not worth tracking the temperature change in the resistor because its mass is such a small fraction of the rest of the mass in the system. The initial copper temperature is 27 degrees Celsius. The initial water temperature is 50 degrees Celsius. And after some amount of time, the system comes to equilibrium, right? At equilibrium, things are equal, right? Or they're not changing with time. And in this case, that means the temperature of everything in our system at equilibrium will be the same. We're told that the resistor adds 100 kilojoules of energy into the system. We're also told that the system is isolated or insulated from the rest of the universe. So in this case, we're going to assume that that insulation is perfect, which means the system is adiabatic. And if you get out your engineering decoder ring, that means that it's perfectly insulated and no heat is transferred between our system and the surroundings. We're required to find the final temperature. So this will be the final temperature of the copper and the final temperature of the water. I suppose also the final temperature of the resistor, but we're not really tracking that because we're assuming that the mass there is approximately 0. We're going to draw a schematic. So our schematic, the textbook is nice enough to give us a schematic of what the system looks like. We have the water in the middle in a copper tank, the resistor over here, and it's surrounded by some kind of insulation. But I'm also going to draw this sort of process diagram. And in this process diagram, I have copper at some initial temperature, 27 degrees, and water at another initial temperature, 50 degrees. I have some energy coming into the system. And then over time, what's going to happen is this copper temperature will increase and the water temperature will decrease, and they'll meet at some steady state temperature. I don't know how much we've used the word steady state, but steady state means that things are not changing with time. And if things are not changing with time, that means that the water temperature doesn't change with time and the copper temperature doesn't change with time. At the beginning of the problem, I don't know if this equilibrium temperature or steady state temperature is going to be in between these two values, up above the water, down below the copper, but I know they're going to come together at some temperature. And that's the temperature that I'm trying to find. One of the things that I'm going to kind of preach that you do is develop these state tables, right? And in a state table, we're going to talk about, what different material do we have at what state, right? What are the properties of that material at that different state? So in this case, we know that initially, right, at state 1, we have two different materials inside of our system: water at 27 degrees, copper at 50 degrees. We've talked about adding quality here, but in this case, we're sort of assuming that there's no phase transition that happens. So we're told that we're liquid water at the beginning. I'm going to assume it stays liquid water, and that the copper is solid. I'm going to assume that it stays solid. If you want, and this, probably becomes more helpful as we start to do cycles where there's more processes, we can also make a process table. The process table says I start at state 1 in this case, and I end at state 2. I give the process some kind of name, and then I see how much heat is added and how much work leaves the system. I want to state and justify assumptions. So in this case, I've said that my system, which contains both water and copper, and the resistor whose mass I'm neglecting, I say that this is an insulated system. And if it's an insulated system, or if it's adiabatic, it means that there's no heat transfer coming into or out of my system as I move from state 1 to state 2. That means that Q is equal to 0 in my first law equation. I'm going to assume that at equilibrium, I have one temperature, temperature 2, which is the same as the temperature of copper at state 2, and the same as the temperature of water at state 2. So at equilibrium, I'm going to assume that all these temperatures come to be the same temperature, because otherwise I wouldn't be at equilibrium. Again, we're usually going to use X to denote quality, but if we're not changing phase, we can also talk about X in terms of what's the phase. So here I'm going to assume that I'm not adding so much energy that I'm melting the copper, right? And I'm not adding so much energy that I'm boiling the liquid. So I'm assuming that there's no phase change here. And I can go back and check, right? So if my T2, I find if it's above 100 degrees Celsius, assuming that my pressure is atmospheric pressure, then that means my water would boil, right? And if it's below 0 degrees Celsius, that means my water would freeze. But here I'm expecting, because we're putting energy in, I'm expecting these temperatures to increase. I'm also going to assume that my specific heats are relatively constant here. So I think this is a reasonable assumption, first, because I'm expecting the temperature changes to be small. The thing about assuming specific heats is that the assumption gets worse the bigger the temperature difference you have, right? So here we're expecting a temperature range of maybe, if I'm saying that the liquid is not going to boil and my temperature, the maximum temperature of the two is I think 50 degrees, I'm assuming maybe a temperature change of about 50 degrees. That's not too much, right? If I was talking about a turbine, I might have, in a jet engine or something, I might have a temperature change, on the order of 1,000 degrees or something, right? So I could have a very, very large temperature difference, right? So because specific heat in real life is a function of the temperature, my assumption about the temperature change, or my assumption about the constant specific heat, gets worse as my delta T gets bigger. I'm going to, because I'm assuming these specific heats are approximately constant, I'm going to assume that I can use incompressible assumptions for delta U, meaning that for both of these, liquids and solids, I'm going to assume that delta U can be approximated as the mass times specific heat times the change in temperature of each specific component. So if I've assumed that the change in kinetic and potential energies are small, then my delta E on the left-hand side of my first law becomes delta U. Now, in this case, because I have two different types of mass in my system, I've split my change in internal energy into two different components. So the change in internal energy of the copper plus the change in internal energy of the water. And that's going to be equal to Q minus W. For my assumptions list, I assumed that the system was insulated. And because the system is insulated, then Q is equal to 0. So I can cancel that out of my equation. I've also assumed that I can invoke the incompressible solid or liquid assumptions for delta U so that M times CV times delta T is equal to delta U. So I do that in both of these cases. Notice I don't just get to pick kind of willy-nilly which temperature difference I'm talking about here, because in the first law, my change in internal energy was U2 minus U1. The temperature change that I have to pick here is T2 minus T1, right? The temperature at the end of my process minus the temperature at the beginning of my process. So in this equation, I know the mass of the copper. I know T1 of the copper. I know the mass of the water. I know T1 of the water. I'm not sure exactly about the work yet, right? We haven't talked about that. And I don't know. I don't think the textbook gave us values for CV, right? So I'd have to look, or the problem gave us values for CV. So I'd have to look in the textbook for CV values. So I found that for copper. I found the metric version of this, because this is a metric problem. So I see that CV for copper is 0.386 kilojoules per kilogram Kelvin. And I found the same value for water. One of the things here is we notice that the specific heat for water is like 10 times bigger than the specific heat for copper. Copper is really good at conducting heat, right? Part of that means that you don't need very much energy to increase the temperature of a given amount of copper a degree Celsius, right? It takes a lot more energy to heat up water, right? That's the idea. The watch pot never boils, right? Now, the part here that could be seen as being tricky, right? So what do I do with that energy that comes from the resistor, right? So my first inclination may have been to call it heat, right? But then I also assumed that the heat into the system was zero, right? So instead, I'm going to call this work, because I could use that electrical energy, presumably, to generate a force, and that force could move something. And a force times distance, that's work, right? So if I call this energy, this 100 kilojoules, into the system, if I call that work, I know from hip to win that work in is negative, right? So here, if my work is negative 100 kilojoules, if I put this up in here, I'd have negative times negative 1 times 100 kilojoules. So this is going to be a positive number. If instead I set this problem up to say that there was no work and the energy came from heat transfer, we would still get the same value, because then I would say that the work was 0 and that the heat was 100 kilojoules, but it was heat in, so it would be positive. So then my Q value would be positive 100 and my work value would be 0. So ultimately, the right-hand side of my equation is going to be 100 kilojoules, whether I call that energy coming in from heat or from work. I just have to pay attention to the sign convention for heat and work, right? So I got to remember hip to win. So if I put these things up in the equation, then the only thing that I don't know in this term is T2 of copper, right? The only thing I don't know in this term is T2 of water, right? And this term I know, right? But I also know from my assumptions, if everything is at equilibrium, T2 of copper is the same as T2 of water, right? Which I can just call T2. So here I could do, because T2 of copper is equal to T2 of water, I can do some isolation here, and I could find the value for T2. And in this case, T2 would be just less than 50 degrees Celsius. So here, this, if we remember, this value, I think the initial temperature of the water was 50 degrees. The initial temperature of the copper was less than that. I think it was something like 27 degrees if I go back here, right? 27 degrees. Oh, no, I mixed those two up, right? So the initial temperature of water was 27 degrees. The initial temperature of the copper was 50 degrees. So I'm still sort of in that range, right? So here, I'm not exactly sure, intuition-wise, does this make sense, right? Because I know there's energy going into the system. I know that the copper should be cooling down, right, which happens. The water should be going up, right, which happens. Although, I guess it doesn't necessarily have to, the copper doesn't necessarily have to cool down because we're putting energy into the system, right? So the intuition for this problem gets a little bit trickier because we're adding energy into the system. You could try to redo this problem to check your model. If there was no energy coming into the system, then you would expect your final temperature to be somewhere in between the water temperature and the copper temperature. And that would be one way to kind of check your model. You're probably not going to take the time to do that on an exam, but here you look at this value and you're at least not, it's not some crazy value, right? It's not like 1,000 degrees Celsius or something, right? Here our temperature is still below the boiling point of water and the melting point of copper. So we know that those assumptions that we were saying that the phase here doesn't change seem to be fairly reasonable. Our delta T's for both copper and water are small. So our assumption that specific heat stays constant is probably pretty reasonable. We're trying to find an answer for temperature, and we got units of degrees Celsius, which again is pretty reasonable, right? So we don't know that our answer is right, but we can't show that it's wrong. And as we've been saying for the last, I guess, couple lectures, you know, that's pretty good, right? So our confidence here is reasonably high. That was all that I wanted to talk about today. Does anyone have questions about the material that we've covered in this class? Or other questions about thermo? All right. If not, I hope everybody has a great couple of days. I will see you on Friday. I will also post the next quiz right after lecture here. So thanks for coming, everybody, and I will see you on Friday at the same time. Bye-bye.